Welcome back, ladies and gentlemen, to another video, AP Chemistry. This is Mr. Kenton here, and it's good to see you guys. Good to be back with you. And we're going to be continuing our work with solutions and aqueous reactions by talking about a chemistry technique known as titration. It's a really important technique that can be used as lots of applications. The one application we're going to specifically be focusing on, at least for right now, would be titration in the context of acids and base reactions, okay? And so that's what we're going to be looking at. Let's go ahead and dive right in, and let's take a look at it. Here we go. So, titration. What you're going to see here, this is the traditional setup that you would have in order to do a titration. So this is thinking of, these are the pieces of glassware, these are the techniques that you would have to consider as you're going through and doing this. And so in a titration, what it typically is going to involve is you're going to take some amount of a solution. In this case, what we're looking at is an acid solution that we don't know the concentration of. We'll say it's an unknown concentration of acid solution. So we've got a set volume. In this case, it's 20 milliliters of acid solution. And what we're going to do is we're going to pipette it into, so there's your pipette. We're going to pipette it into an Erlenmeyer flask. Okay. And so you've got your acid solution that's being placed into your Erlenmeyer flask. And the acid in this particular case, because it has an unknown concentration, we're going to refer to it as the analyte. That is the thing that we're trying to determine. That's what we're analyzing in this titration process. Now, the way titration works, you've got this unknown. We know it's an acid, so one thing you can do is you can react it with a base. And so what you can do is you can use a standard NaOH solution. Now, what that means is that you've got a solution of sodium hydroxide that you know the concentration of, right? And so this standard sodium hydroxide solution would be what's known as the titrant. That's the thing that you know the concentration of. And so what you've got, or what you would use in order to carry out a titration after you've pipetted your acid into your Erlenmeyer flask, is you're going to place your standard sodium hydroxide solution into a piece of glassware called a burette. Okay, and so a burette is a piece of glassware that allows for you to dispense very precise quantities of a solution at a time, right? And so the way it would work is it has an opening and closing valve called a stopcock. And so what that will allow you to do is to dispense the sodium hydroxide solution into the acid solution. Now, when it comes to titration, one thing that you'll need to keep in mind is that when you're using the burette, the best thing for you to do before you carry out the titration is what you do is you take some amount of sodium hydroxide and you would place it inside of the burette. And what you would do is you would want to coat the inside of the burette with that sodium hydroxide solution. And you might be asking yourselves, well, Mr. Kenton, why would I want to do that? And the reason is really simple. We want to make sure that when we're using our burette, the only thing that's being dispensed is the sodium hydroxide solution. So what you would do is you would do that a couple of times, right? Maybe 2 or 3 times. You take a little bit of sodium hydroxide solution that you're going to be using, you'd place it inside the burette, keep the stopcock closed so it doesn't fall through, and then you would kind of slowly rotate the burette so that the inside is being coated with the solution that you're using. And what that's going to do is that's going to help eliminate errors that could be caused by leftover solutions or maybe even leftover water that could be in your burette. Okay, and so, you know, once you're ready to go through the titration process, you would fill up your burette. And the neat thing about the burette is it starts with its volumes. You would read it from the top. You would start at a specific volume, and then typically up at the top is 0. And then as you dispense, you would be able to take the difference from where you started and where you ended to calculate the volume of the sodium hydroxide, in this case, that was dispensed. Now, in a titration process, you notice from B to C, there's a color change that's taking place, and usually that color change is made possible because an indicator has been added to the solution that's going to be able to pick up on changes in pH that are going to occur as the base is being added to our unknown acid, right? And so that's a real kind of quick overview of the titration process. And I believe Mr. Lamberth and I have some simulations, or at least some virtual labs or things that we can share with you guys so that you can see this process being played out. So be on the lookout for those. So let me kind of move forward here. Now, there were some things that I introduced that I talked about on the previous slide that I just want to revisit, right? So in a titration, you've got two substances. You've got what's called the titrant. That's the substance that has a known concentration. And your titrant is going to be the substance that goes into your burette. Now, if you're thinking about the previous slide, that would have been the sodium hydroxide solution, right? That was our titrant. That was what we knew the concentration for. The next substance is the analyte. And your analyte, this is the substance that has an unknown concentration. So this is what you're trying to figure out. You're trying to identify the concentration of this analyte by using the titrant. Now, this is the substance that is going to go into your Erlenmeyer flask. Okay, so in reference to our previous slide, that would have been the acid solution that had an unknown concentration. That's what went into the Erlenmeyer flask. Now, when we start talking about titrations, there are 2 points that we need to be familiar with. The first of which is the equivalence point. And the equivalence point can be defined as the point that occurs when the analyte has been completely consumed by the titrant. And so if you think about that, what we're communicating is we've just said that we've completely consumed the titrant. We've completely consumed the analyte. So we think about that 20 milliliters of acid that was in that previous example. What we're saying is that we have completely reacted all of that acid. And so in a sense, what we're saying is that there is we've allowed the reaction to go to completion, right? And so that's when we would have equal moles of acid and base that have, in a sense, that have reacted, right? Now, the other point that is listed here is the end point. Now, the equivalence point is really hard to get to specifically because it requires such a precise amount of substance to be reacted in order for that to happen. And so what chemists use is an endpoint. They use an indicator to help signal, to provide a visual cue that the titration is complete, right? And so an endpoint is an observable point in a titration that signals to a chemist that the analyte has been completely consumed. Now, that means that the equivalence and the endpoint are not the same thing. So the equivalence point occurs when all of the analyte has been consumed. The endpoint occurs once the indicator acknowledges, if you will, that all of the analyte has been consumed. And what we tend to find is that tends to be slightly above or slightly below the equivalence point for a given process, right? And so indicators such as phenolphthalein can be used to help facilitate this process so that chemists can know, hey, I've reached the endpoint, or I've at least gotten to or have passed my equivalence point in this particular process. Now, on the next slide, you're going to notice that there's a pH. This is a titration curve. And with titrations, obviously the thing that chemists are looking at over time that's changing is they're looking at the pH, which is simply a measure of the concentration of the H+ ion that's in solution. And so this can occur 2 ways, right? You can do a titration where your analyte is an acid, or you can do a titration where your analyte is a base. Okay, now in the scenario that's on the left, we're using a titrant that is a base, and our analyte is the acid. And so what we can see is that over time, as the base is being added, obviously it's acidic, so it's got a pH that's less than 1, or less than 7, excuse me. And what we see is that pH starts off low, but then as the base is being added, we see that that pH is increasing, right? And then all of a sudden, we hit this point at which there's this steep increase. And you'll notice that both of these graphs have taken time to kind of notice or hone in on this pH value of 7, which would be our neutral pH. And that would represent our equivalence point in our titration. When the acid and base have neutralized each other, that's when we've reached our equivalence point. Okay? And then, obviously, as more and more base is being added, there's a shift, right? So now there's less acid, and now there's way more base that's left over in the solution, right? Now, likewise, on the right, it's the flip, right? We're starting off with, we're adding acid to a base, so we're trying to figure out the concentration of the base. So it starts off with a high pH, and as acid is being added, we see that decrease in pH, and then we get that sharp dip. Again, we've neutralized it. We're at 7, so that's when the reaction is neutralized. And then as excess acid is being added, we have a lower and lower pH that's taking place. And so as you're even looking at these graphs, something that I want you guys to consider is what particles are present at the beginning, kind of at the middle, at the equivalence point of the titration, and then what's kind of left over once excess of one substance has been added. And if you think about that, like for our situation on the left, initially when the reaction has not started, so you've got your analyte in the Erlenmeyer, and you've got your titrant in the burette, currently in your Erlenmeyer flask, you have only the acid. So what you would see present would be a bunch of H plus and Cl minus ions, at least according to this particular representation. And then as you are moving across, as you slowly are adding that base, you're going to have what's going to happen is all of the base is going to be consumed, and you're still going to have leftover HCl. And that's going to continue up until you get to the equivalence point, right? So because once we get to the equivalence point, what's going to happen is that the amount of acid and base that have been added are going to be completely consumed. So at that pH of 7, what we would anticipate seeing is that we would have, in this case, it would be all H2O and NaCl, right? That's assuming that we stopped at that particular point. Now, as soon as you add an additional drop or add more base, what's going to happen is you're no longer going to have, you'll have your NaCl and you'll have your water that was produced in that particular process. But then what's going to happen is as you continue to add additional sodium hydroxide, what you would have is you'd have some additional sodium ions as well as some hydroxide ions that are floating around inside your solution once you moved up past that equivalence point, right? Now, looking at the other side, what you would have happening is you'd start off with only Na plus and OH minus that are present. As you're adding acid, what you would see happening is that there'd be no H plus and Cl minus, but the amount of Na plus and OH minus is going to decrease as the titration happens. You hit your equivalence point again, and so then you would have NaCl and H2O that would be present in your Erlenmeyer, and then at the equivalence point. And then once you go past the equivalence point, you'd have your sodium ions, you'd have your chloride ions, but as you begin and your water, but as you begin to add more acid, you would then start to see the presence of H plus ions, excess H plus and excess or more Cl minus ions. Now, I hope that makes sense, just thinking it from that particle representation. And that really covers what you need to know from a conceptual standpoint of what a titration is. What I'm going to be doing is I'm going to be making a separate video that's going to be paired with this one of approaching a problem where you guys are having to solve a titration and essentially trying to figure out what's that equivalence point, at what point is this reaction being neutralized. So be on the lookout for that. Thank you guys for taking the time to join me today. I really do appreciate it. If you do have questions, please don't hesitate to ask. Fill out that Google form once it gets posted, and I'll try to address the questions as best I can. Thank you guys so much. Have a great day.